Hey, and welcome back to DATQVAULT video lectures. In this video, we're going to talk about orbital hybridization, and specifically, we're going to talk about orbital hybridization of carbon in particular. This is because carbon is the central element in organic chemistry, and basically, without carbon, you're not going to form any kind of organic molecules. So, we're going to start with the hybridization of carbon. So I just wanted to remind you guys to make sure to be an active learner. Take notes while you're watching these videos. That's why we provide a study outline for each and every single lecture in this lecture series. So even if you don't like reviewing notes, there's a lot of research out there that actually shows that memory is increased dramatically if you write, listen, and watch all at the same time. So the mere act of writing can improve later retention. So highly encourage you guys to, use the outline or just have a piece of notebook paper out and take notes on these lectures. So again, we're going to start with the structure of methane when we're learning about orbital hybridization of carbon, as it's just commonplace to start out with the most simple carbon molecule. So here we have the structure of methane. So let's talk about methane for a minute. We all know that methane has 4 bonds to hydrogen. In general, we know that carbon forms 4 bonds pretty much to any particular atom that we want it to. Also, the bond angles in methane, so the distance or the angle between 2 hydrogens in methane is 109.5 degrees. So these are 2 really important things that we need to remember about methane when talking about orbital hybridization. The next thing we should look at is the electronic configuration of carbon itself. So in carbon, the electronic orbitals of carbon, we have the 1s orbital, the 2s orbital, and then we also have the 2p orbitals. We know that the 1s orbital is completely filled. And then we move out to the outer shell of orbitals, which is the valence orbitals, right? So in the valence orbitals, we have the 2s and the 2p orbitals, which I have shown here. So using Hund's rule and the buildup property, we're going to start putting electrons into these orbitals. First, we fill up the lowest energy orbital first, spin pairing our electrons. We know that carbon has 4 valence electrons. So next we're going to put the next 2 valence electrons up into the next highest energy orbitals, which are these 2p orbitals. Remember, there's 3 2p orbitals, the px, py, and pz orbitals. So this is what the ground state configuration for carbon looks like. So there are a couple discrepancies now that we notice between the structure of methane and also the electronic configuration around this central carbon. So what are the differences? The main difference is we know that using valence bond theory, if you don't remember what valence bond theory is, please go back to the lecture on molecular bonding and review that really quick. But valence bond theory tells us that in a chemical bond, in this case between hydrogen and carbon, we need to have 1 unpaired electron in an orbital of each of these atoms to form a chemical bond. If we notice that carbon in this electronic configuration only has 2 unpaired electrons in the 2p orbitals. So based on this model, we can only form 2 bonds around this central carbon. We know that carbon creates 4 bonds, especially seen here in the structure of methane. So that does not really mesh well with these two different theories. So we have to do something to fix this, and this is where orbital hybridization comes into play. Alright, so here we have the electronic configuration on carbon. If you remember, the 2s orbital is filled, and we have partially filled 2p orbitals. So just to get an idea of what these orbitals look like, a 2s orbital, if you remember, is circular. In this case, our 2p orbital is going to be, our 2s orbital is going to be filled. P orbitals look like this. We have 3 of them. This is the 2px, 2py, and 2pz. We call them x, y, and z because One of them runs along the x-plane, one of them is perpendicular in the y-plane, and then one of them is perpendicular, both of those, in the z-plane. When we combine all these 2p orbitals together, this is kind of what they look like. And we have 2 electrons in these 2p orbitals for the ground state electronic configuration of carbon. So now we notice that we're not going to be able to get any kind of chemical bonding to 4 different atoms around carbon if we stay with that electronic configuration. So the first thing we could do to actually help create 4 chemical bonds is, instead of having 2 electrons down here in the 2s orbital, we could actually promote one of these electrons from the 2s orbital up to the 2p orbital. So now we notice that we have still 4 valence electrons, which is what carbon contains, but now we have 4 unpaired electrons, which can now participate in 4 chemical bonds, for instance, to hydrogen. But this still doesn't tell us one other important thing about, for instance, the bonding in methane, is that each bond angle is 109.5 degrees, which means that methane has a tetrahedral shape. If we tried to make a bond to the 1s orbital and then these 2p orbitals, we're not going to form a tetrahedral shape whatsoever if you remembered what the 1s orbital and 2p orbitals actually look like. So we have to do one other thing, and that is to actually hybridize these orbitals together to get 4 what are called degenerate orbitals. So degenerate orbitals, the word degenerate means these orbitals are all of the same exact energy. And because they're same exact energy, they have the same exact shape. These, such as the 2p orbitals, are also degenerate. But now we have 4 of the same orbitals. They are called sp3 hybridized orbitals. And this just comes from the combination of this s orbital and these 3 2p orbitals. Alright, now we need to know what exactly these sp3 orbitals look like and why do they give us the tetrahedral shape that we see in methane. So here we have the 2s orbital, and then here we have one of the 2p orbitals. So as I stated before, just to get our sp3 hybridized orbital, we're actually going to combine together this s orbital and one of these 2p orbitals. So if we do that, we can just think about it as the s orbital overlapping with this 2p orbital, and if we do that, we get an orbital like this where one of the lobes is going to be bigger than the other lobe. So of course these 2 orbitals here are in phase, and then the other lobe is going to be out of phase, something like this. So of course the in-phase orbitals are going to combine together and become a larger bonding orbital, and then the smaller orbital over here is going to be the anti-bonding orbital of this sp3 hybridized orbital. So here's our sp3 orbital. We get 4 of these because we have 1 s orbital in the carbon electron configuration, and we have 3p orbitals, and they're going to combine together to form 4 sp3 orbitals. Now, using the Vesper model, we can actually form the tetrahedral shape. So first we're going to quickly review everything that we just did. We took the 2s orbital, and here we have the 2p orbitals. This is the electron configuration. What we did first was we promoted one of these electrons from the 2s orbital up to the 2p orbital. So now we have 4 unpaired electrons. Once we did that, then we hybridized these orbitals together to give us 4 orbitals, 4 degenerate orbitals, known as sp3 hybridized orbitals. Remember that a hybridized orbital, sp3 hybridized orbital, kind of looks like this. If we combine together these sp3 hybridized orbitals using VSEPR theory, which means we want these orbitals to be farthest apart from them as possible, we get this tetrahedral shape where the angle between each of these orbitals is now 109.5 degrees, which is exactly what we see in methane. Each of these orbitals now has one electron in them, which is able to bond with an electron of an orbital of another atom. Alright, now let's form our methane molecule using our sp3 hybridized orbital of carbon, and now we have our s orbital of hydrogen. So this is a hydrogen 1s orbital. It has one electron in it. So we match the spin states in each of these orbitals of hydrogen and now of the sp3 hybridized orbitals of carbon, and we can form our methane molecule. So here we have now our 4 hydrogen s orbitals bonding to our 4 sp3 hybridized orbitals around carbon, and each orbital has 2 spin paired electrons in each bond. Alright, so this is the basis for orbital hybridization around carbon. So this can be used to make multiple different molecules. So this is methane. This is the most simple example. So what I want you guys to do right now is to draw the sp3 hybrid orbital diagram, kind of like I showed you in the previous slide for methane. But now I want you to do it for ethane. So we're just adding another carbon to the mix, and we're adding 2 more hydrogens to the mix. So I want you to pause the video for a second, try to draw the hybrid orbital for ethane, and then we'll draw it out together. Alright, now that you've had a second to draw out what you think the hybrid orbital looks like for methane, we'll draw it together. Sorry, ethane. So let's first draw out what ethane actually looks like. 2 carbons, 6 hydrogens, looks like this. Every single bond in ethane is a sigma bond, and each carbon is going to be sp3 hybridized because it has 4 different bonds to it. And each carbon is also tetrahedral in shape. Alright, so first we're going to start by drawing the orbitals of carbon. Here, so this is a tetrahedral carbon, and then we have 3 hydrogen s orbitals bonded to each of these sp3 orbitals around carbon. So here we have a hydrogen 1s orbital, and here we have a carbon sp3 orbital. And we have 1 electron from the sp3 orbital and 1 electron from the hydrogen 1s orbital to go into making a bond. And this happens for each of these other orbitals as well. So now we have our other carbon atom, and we have, again, our sp3 hybridized orbitals around carbon, and we have, again, the hydrogen 1s orbitals. The only difference from ethane and methane is now we have a carbon-carbon bond instead of an extra carbon-hydrogen bond. So instead of the hydrogen 1s interacting with the carbon sp3, now we have 2 carbon sp3 orbitals interacting, each of them containing 1 electron, and they're going to form another sigma bond. Alright, let's move on to other carbon hybrid orbitals. This time we're going to look at sp2 hybridized carbon orbitals. So an example of this would be ethylene. So the only difference between ethylene and ethane is we're missing 2 hydrogens, and now we have a carbon-carbon double bond. So what happens between an sp3 hybridized orbital and an sp2 hybridized orbital is we basically break up this sp3 hybrid to form 3 sp2 orbitals coming from 4 sp orbitals, and then we form 1 p orbital. Why does this happen? It's because if we look at the orbital diagram of ethylene, one of the bonds between carbon, this bond right here, is going to be a sigma bond, which is going to be one of the sp2 hybridized orbitals. And then the other bond is going to come from the p orbitals that we made from this sp3 hybridized orbital, and the interaction of these p orbitals between these two carbons are going to go into creating what's called a pi bond. So each of these p orbitals, remember, have 1 electron in them, and they're going to go into forming the second bond between these two carbons. So in ethylene, we have between the two carbons, we have 1 sigma bond, and we have 1 pi bond, which comes from the interaction of p orbitals, not the interaction of any kind of sp hybridized orbital. Alright, let's look at the electronic configuration of sp2 hybridized orbitals. So here we have our degenerate sp3 hybridized orbitals. Each of them has 1 electron in each of these orbitals. And now to go to form an sp2 hybridized orbitals, like I said previously, is we basically split up this sp3 hybridized orbital into 3 sp2 hybridized orbitals and then 1 p orbital. And again, each of these orbitals contains 1 electrons. Now we notice that we form around an sp2 hybridized carbon, we have 3 bonds. 2 of these are going to go into sigma bonds, and then one of these sp2 orbitals and the other p orbital are going to go into the double bond between the two carbons. So, takeaway message for sp2 hybridized carbons: they are used in double bonds, and the geometric configuration around a double bond is always going to be trigonal planar. So we're no longer tetrahedral, we go to trigonal planar. This is because we form a p orbital, and then that p orbital will then interact in what's called a pi bond. And these sp2 hybridized orbitals still participate in sigma bonds. Alright, so let's go to sp hybridized orbitals. So we know how to get from an sp3 to an sp2 hybridized orbital. Now we're just going to go by the same kind of method, going from an sp2 orbital to an sp orbital. We're basically gaining another p orbital, and we're losing an sp hybridized orbital. An example of this would be ethine. So again, this time we're going to start with our sp2 hybridized orbital, and we're going to break it apart just like we did with the sp3 hybridized orbital. We have now an sp orbital and another p orbital. So this might be a little bit confusing, so if I want to pause the video and take a look at this for a second. We basically have now 2 p orbitals around each of the carbons, and each of the carbons also is participating in a sigma bond. Our sigma bonds are here between carbon and hydrogen, and carbon. These are the sp orbitals participating in these sigma bonds. The p orbitals are these orbitals here, and also the other p orbital is completely perpendicular to the first p orbital in an sp hybrid orbital. These orbitals interact with each other like this and like this to form now 2 pi bonds. So in ethylene or any kind of carbon-carbon triple bond, we have 1 sigma bond between the two carbons, and now we have 2 pi bonds between these two carbons. Alright, so what does the electronic configuration look like around these new sp hybrid orbitals? Again, we're going to just start from the sp3 hybrid orbital, and now instead of promoting one of these sp3s to just a p orbital, we're going to take and promote two of these sp3 orbitals to two p orbitals, and now we're left with two sp hybridized orbitals. Again, we're going to fill in the electrons, one in each orbital. Alright, so the takeaway message for sp hybridized orbitals around carbon is they're going to participate in triple bonds. These p orbitals participate in pi bonding just like they did in sp2 hybrid orbitals, and these sp orbitals participate in sigma bonds. The geometric configuration around an sp hybridized carbon is going to be linear. So the bond angles are going to be 180 degrees. Alright, let's practice some of the stuff that we've learned in this lecture on orbital hybridization. So here we're asked how many sp2 hybridized carbons are in this molecule. You might see a question like this in the DAT. So why don't you take a second, pause the video, try to answer this question, and then we'll solve it together. Alright, now that you've had a chance to answer this question on orbital hybridization, let's go through it together. So let's kind of quickly jot down what we know about sp2 hybridized carbons. We know that they participate in forming double bonds. You don't have to form just a double bond to a carbon. You can also form double bonds to oxygen, nitrogen, pretty much any other atom. Also, we know that sp2 hybridized carbons, the geometry around them are trigonal planar. So let's look at each of these carbons and see which ones fit this bill. This carbon right here, bonded to oxygen, has a double bond to oxygen, and the geometry is trigonal planar. So that one's definitely sp2 hybridized. These two carbons here are bonded to 4 different atoms apiece, and the geometry around them is tetrahedral, and there's no double bonds. Those are actually sp3 hybridized carbons, as are these two right here, and also this carbon right here. So those are all sp3 hybridized tetrahedral carbons. So if we look at this carbon right here, it also has a double bond. It's bonded to 3 other atoms. The geometry around is trigonal planar, as sp2 hybridized, and this carbon also fits the same bill. So in this molecule we have 3 sp2 hybridized carbons. Alright, so this kind of concludes this lecture on orbital hybridization, specifically targeted at carbons. Remember, not every single topic we cover is going to appear on your specific DAT exam. Standardized tests are totally randomized samples, and each test is going to be completely different from one another. However, the greater exposure you have to the breadth of material potentially covered on your specific DAT, the more likely it is that you're going to score very well. And I can't emphasize this anymore, a difference of 1 to 2 points on the DAT is going to really differentiate you from the rest of the test takers, and you're going to have a much better chance at getting into the college of your choice. So really focus on learning, and more importantly, comprehension of this material.